So I'm sorry for my voice, but I guess it's a sort of allergy problem. I believe it's Brexit allergy, maybe. I don't know. Who knows? I hope you will be able to follow my talk. So I would like to present you some results we have about vessel detection for angiogenesis quantification, which is an interesting problem. You may all agree with me, I guess, for cancer assessment in general. And it's very interesting to try to quantify this from the digital pathology, because you get much more sensitive information and precise, hopefully, information. But as you may know, the detection of this kind of features, it's quite challenging, because you have different shapes. The morphology is very complex, and the densities are different. So as you see in the few examples, I try to select. So what was the way in which we tried to do that? We would like to work with two methods. For the vessel segmentation, which is somehow the first step we would like to achieve for this objective, not only work with one family of method, which most of you are working with nowadays, discriminative, but trying to put in something a bit more generative. So you may have heard about this kind of classification, which is a high-level classification of the methods, where in the first part, in the first class of methods, you try to understand what's happening. In the second one, you just try to assess. For example, this is a generative approach. If you would like to understand how the EBS is working, right? But if you just want to use it, you don't need to understand it. This is a discriminative approach. This is what neural networks are doing, right? So you have a lot of methods in each of them. This is the generative family, in which you have a lot of probabilities, conditional probabilities, and discriminative models, which are more based on neural networks and deep neural networks nowadays. So the idea is now that if we would like to use only the deep neural network for that, we will need probably a lot of annotation from you guys. So I know this is a tedious work. We all know that this is almost impossible in the quantity we like to have as engineers, as software engineers. So the idea was to try to find a compromise and to work with different images. So like masks, like simulated images, like images created in another way. So the methods we are talking about are like from those two families. Like the first one, I was talking about networks. And this one, the second, which is trying to understand what's happening, which is based on rules and use like Markov processes. And I would like to describe the process we try to use for that purpose, which I did use for other purposes in the past, which is the market point process. So the idea is to do a sort of recurrence in which we build shapes, we put them in the image, we try to evaluate them, and then we do it again. We keep the one who are good, and we kill the other one who are not good. And we reach something which is convergent. So this kind of algorithm is proven to be convergent in continuous space. In this discrete space, which is the one we are working with, of course, we need to tune it properly, but it's usually going quite well. So the idea is to create shapes. The shapes we create are according to the one we are looking for. And you just take off the one who are not fitting, who are not having the good energy. you keep the green ones, you create another wave, you keep only the blue ones, and so on and so forth. We did that for neurite detection. You have different kind of energies, elements here, which is like, maybe I will not describe too much in detail, but I can do it if you would like to. Data energy interaction prior, and spatial configuration information. And this is something we did in our case for neurite detection and for the nuclei detection in digital pathology. The advantage of this kind of method is that it's completely parallelizable, because you only work in a neighborhood of one shape. So the use of the GPU is highly recommended. The MPP principle in our case for the vessel detection, it's very simple. It's something which is like that. You have the vessel here, and you have something which is good. This one, it's maybe better than that one, the blue one than the yellow one because of the intersection. And of course, this one it's not recommended. So the data we worked with coming from this work published in 2011. And we did define a sort of strategy for this market point process. We defined the distance we will use for the contrast predictor. And what is interesting is that we are working with heterogeneous and quite noisy images. So now, from the point of view of the distance, which means a contrast, and the overlapping predictor, which is giving the overlapping between the shapes, we are looking to find something which is having like this kind of configuration with a good detection, with the two elements, G and K, computed here quite low. And I will maybe not go too much into details, but this is the way in which things are working. The CNN is not leading the approach. It's more like collaborating with the MPP. So you have some of the parameters, which are like distance, Bhattacharya distance, which is very well known in Markov processes, which can be adjusted using the CNN. And then you have the Jacquard index, which is also adjustable by the MPP process. And you have this kind of backpropagation. The neural network we used is inspired from this work from 2018, sorry. And this is a sort of information about the contrast predictor we used, about the overlap predictor we used, and what is interesting too is that we can work with limited samples. We don't need a lot of annotation. So we did manage to improve the previous work, which has been done in 2018 only with the CNN, from the point of view of the accuracy, precisely, which is very bad for this kind of applications. It used to be like 0.1. Now we are reaching something around 0.5. Still a long way to go, but that means that this is the state of the art, right, in this area right now. So you have here the evolution of the mask. The masks are created inside and outside because you have a border effect you need to consider. And this is the epoch evolution until you reach something close to the vessels you would like to detect. This is the evolution of the loss function. As you can see, we have a sort of stability, and then the distribution of the cases for the three type of images I was showing you are distributed more or less in the direction we would like to. We say that we are reaching something quite low in terms of values. So that's it about the work. What has been done is to use few labels for the training to complexify the environment, test the scalability. The CNN MPP collaboration is going quite well for noisy and heterogeneous images. We compare other methods like UNet for the learning base and other rule-based methods like active contours, and it's working quite well. So it's a framework which can be generalized. And in the future, of course, we'll go for more complex shapes, like the one you see here and here. So Umema Laifai is the lady doing her PhD on this topic, so hopefully we'll have her PhD coming out this year. She's working in a collaboration between me and my old fellows from Singapore. And last but not least, I would like to remind you to come to MICAI 2020 in Peru, which we will proudly organize with Anne and a lot of other fellows, maybe some of you too. Thank you very much.
Thank you very much, Daniel. Very nice work. Does anyone have any questions? So I have a sort of general philosophical question. So you've shown very nicely that if you combine traditional computer vision, mathematical approaches with a CNN, you get quite nice results. Do you think that that will always produce better results than a pure CNN, or do you think that if you did have a very large supply of labeled data that eventually, and a large enough capacity model, that the CNN approach would eventually beat the expert plus CNN hybrid?
I personally believe that the CNN is working very well only when the things are very well delimited, defined, and limited. If you have a very complex situation like this one, it was obvious for us that the help of the probabilistic methods and the one describing a bit more the knowledge about the area we're working on, it's still very useful. And I deeply believe that we should not forget the other methods. This is why I'm always defending this kind of combination, as I did for the semantics also, with the deep learning and other technologies we should keep on the roadmap, in my opinion.
Yes, we have a question there.
You've been using your model, using H&E sections mainly for your model. I'm just wondering if you'd consider using immunohistochemical stains highlighting the endothelium of the blood vessels, so CD31 or 34, the typical markers. And that's just one question. And the second question is that there are some tumors where the vascular patterns within the tumors are prognostic. So whether you can move forward, obviously you're looking at the regular vessels at the moment, and then you're going to look at more unusually shaped blood vessels, but then moving forward even further, perhaps you should be looking at the vascular patterns within the tumors and whether they can help you predict the outcome of the patients.
Yeah, I believe it's a very good advice, and I take it as a good one. And you are right, perfectly right, because once we are able to make a good detection, we need to have a better understanding of what's happening inside, and we'll definitely try to do it according to the means we'll have. Concerning the immunohistochemistry, the database we used and the models we used were inspired by the characteristics of both. Right now we did it just on H&E, indeed, but I guess the same kind of method could be used for the sort of fusion of modalities in the future.